Example 6.5. The goal. Combine the concepts of conservation of energy and conservation of momentum in inelastic collisions. The problem. The ballistic pendulum, figure 6.12, I was going to say B, but it looks like it's 6.12a, is a device used to measure the speed of a fast-moving projectile, such as a bullet. The bullet, mass 1, is fired into a large block of wood suspended from some light wires. The bullet embeds itself in the block, and the entire system swings up to height h. Boop. It is possible to obtain the initial speed of the bullet by measuring h and the two masses. As an example of this technique, assume that the mass of the bullet, m1, is 5 grams, the mass of the pendulum block is 1 kilogram, and h is 5 centimeters. Part A, find the velocity of the system after the bullet embeds in the block, and Part B, calculate the initial speed of the bullet. So there's actually two parts of this problem. In Part 1, the mass of the bullet and the mass of the pendulum connect, and the conservation of momentum is used. However, energy is lost because of the combination of the block and the mass, the block and the bullet mass. On the second part of the experiment, phase 2, the mass of the bullet and the block rise to height h. During that period of time, there's not going to be very much energy lost to friction, so we will say that that energy is conserved. So which one of these should we handle first? The first one is that m1 v1 plus m2 v2 equals m1 plus m2 v final. So we can switch this to m1 of 0.005 grams times v1. We don't know what that is. We do know what the velocity of the block is, which is 0. Then we will take 1.005 times our final velocity. And so that gives us the ratio between our final velocity and the initial velocity. But we don't know either of those yet. The other equation that we got is that the kinetic energy of the system initial, which is 1/2 m1 plus m2 v squared, is equal to the kinetic energy of the system final, which is going, well, not kinetic energy, sorry, potential energy of the system final, because the block is going to stop. So that's going to be m1 plus m2 8, or GH. So that'll be 1/2 times 1.005 V2 equals 1.005 times 9.8 times our 0.05 meters. So this only has one unknown, so we can solve for that one. Taking this and dividing by this, I got V2 equals 0.98 meters per second, or that's V final from the first part of the equation. Oops, I forgot the squared. V2 squared, V2 squared, V2 squared is 0.98. Square root of 0.98 is basically 0.9899. So V2 equals 0.99 meters per second. And I changed the notation. That was called V final before, so this will be 0.99. That's the velocity of the block and the bullet after the collision. So 1.005, and divide that by 0.005. And we get 198.98 meters per second, or rounded up to 199 meters per second. Question 6.5. List 3 ways that mechanical energy can be lost from the system in this experiment. And that is when the bullet hits the block. There's going to be 3 things. They're essentially sound, heat, and the deformation of the block. Because you can kind of use that formula 1/2 kx squared to find out how much energy it takes to go to deform the block, but that that energy does not come back unless the block is elastic. So whatever 1/2 kx squared doesn't come back elastically, whatever energy doesn't come back elastically is lost to the system. Exercise 6.5, we got a 5-gram bullet fired horizontally into a block of 2 kilograms. This string isn't supposed to be there. It's just attached to a horizontal spring with a spring constant of 600 newtons per meter and a distance of 6 centimeters. I think this time I will use F for final and M for middle. Middle will be after the collision of the blocks, and final will be after the spring contracts. So the potential energy at the end is going to be 1/2 kx squared, and the kinetic energy in the middle is going to be m1 plus m2, 1/2 m1 plus m2 v middle squared. So there's just one unknown in that equation, and solving that gives you v middle equals 1.04 meters per second. And then we can apply conservation of momentum in the first collision. M1v initial plus M2v initial equals M1 plus M2v middle. And this is V1 initial and V2 initial. This part is 0 because the block is not moving, and this will be 0.005 times V1 initial. No, we don't know that yet. V1 initial plus 0 equals 2.005 times 1.04. And then we divide this quantity by 0.005, and we get 417 meters per second.